Hi friends, it's Ben yet again. This is a video for the differential equation, the differential calculus class. I am attempting to talk about rate of change and higher derivatives. This will be the third, fourth attempt at this. I've been interrupted by children. I've been interrupted by dogs. I've been having trouble with doing basic arithmetic. I've resorted to a script, which is something I dearly hate to actually have to resort to on these things. But in this particular case, I have to do the calculations ahead of time because I'm sorry, folks. It's been a long day. So anyway, we will just jump right into it because this is the final take, no matter how it turns out. Oh, good. My computer needs to install a plugin before it can accept the shared screen. Come on, screen. Do it this time. All right, there we go. So when we talk about functions, we have talked about that the derivative of a function at a particular point will represent the slope of a tangent line there. As you all should know, then the slope of a tangent line is going to be, if you increase your x value by 1, how much your y value will increase by. If it's negative, then make it decrease, but so, all right. So that's our big thing to talk about with rate of change. So far, we've been talking a fair amount about when f prime is positive or negative, we'll get either increase or decrease. So the thing we're about to do here, we're going to see something where we have a particular rate of increase or decrease, not just that it's positive or negative. And there's this phrasing about a marginal rate of change being something that we might refer to as dy or df. And it's going to be the change in f when the x value changes by 1, okay? So if you make reference, as in the next example, how much does it cost to produce the 2001st bagel? Then that means you have to be dealing with the slope of the tangent line, not where x is 2001, but where x is equal to 2000, because at x equals 2000, you'll be increasing by 1. See? All right. Anyway, this marginal stuff, we talk about marginal cost, marginal revenue, marginal demand, all kinds of stuff shows up in economics where they refer to things as being marginal. Essentially, it just means what's the derivative? Along those lines, if you ever hear somebody talk about a marginal tax rate, they are being a little bit deceptive, because marginal tax rate is going to be essentially the derivative of the tax rate, not the tax rate itself. So, All right, so the production cost of X bagels, so this function 300 plus 0.25x minus 5 times 10 to the negative 10th x cubed. Where on earth does that come from? I do not have an answer for you. I can tell you from looking at it that the 300 makes sense to be the setup cost for the day. You're going to pay your bakers to be there anyway. You're going to turn on the ovens anyway. No matter how many bagels you actually get out, it's still going to cost you $300. And then maybe the materials for every bagel is going to cost 25 cents. Materials, yeah, you know what I mean, flour, yeast, and so forth. This part here, that is a mystery to me. I've had people try to explain it to me, and I don't quite get what's going on with it. But it does have some sort of suggestion that has something to do with the economy of scale. If you were handcrafting one bagel at a time, it would not be as expeditious as baking 20 of them in the oven at once. So all right, so we are going to estimate the cost of the 2001st bagel. So what we'll have to do there is to get C prime. So C prime, you're going to get the 0 from the 300, and then a 0.25, and the derivative of x is just 1, and minus, now the 5 times 10 to the negative 10th is just a constant. times 3x squared. So if you'd like, that could be 0.25 minus 1.5. Oh, y'all like to use the E notation, don't you? E minus 9x squared. I prefer to use times 10 to the minus 9th, but I know the calculators show it a different way. So what we're looking to do on this is to calculate C prime of 2000. As I said before, not C prime of 2001. C prime of 2001, when you increase that, the 2001 by 1, that would get you the 2002nd bagel, not the 2001st. So anyways, we plug in here and we will get 0.25 minus 1.5 E minus 9 and times 2000 squared, okay? And I went ahead and did this with the calculator and I came out with not that, 0.244, so 24 and 4/10 cents, okay? If on the other hand, you were to just go in and say C of 2001 minus C of 2000 and see what you came out with. And again, I did this by hand before. I get 0.25 minus 0.006003 0005. So that's going to be approximately 0.243 997. Okay, so as you see, it differs from our estimate in like the 6th digit past the decimal. So pretty good estimate. Okay. So in general, we tend to use all of these things here with the marginal costs when we're doing actual theoretical stuff for modeling, because you can get the calculus to do things for you that you would have to have lots of extra information and lots of extra computing power to get the exact values for it all the time. Additionally, this here, these modeling functions, they're estimations, okay? So once you start dealing with an estimation for this, then dealing with an estimation for your rate of change there, kind of makes sense because it's not going to make that much difference, right? All right, so let's take a look at another example here, and this one has a demand function for oil. I made mention of this previously, that when you talk about demand functions, they need to be something that's decreasing. And generally, we usually use something linear because it's easy to work with, but they just need to be decreasing. And in general, you don't know the actual function, but pretend we do, and then pretend that it's this. So if we're going to find the change in demand as P goes, the price goes from $40 to $41 a barrel, then we can go in here and say D of P, or D prime of P. And so if you think about that as being 900 P to the minus 1, that makes this a little bit easier to deal with, because then you get minus 900 P to the minus second, or equivalently minus 900 divided by P squared. So D prime of 40 is going to be minus 900 divided by 40 squared. So that would be minus 900 over 1600 and 9/16, which I ought to already know what it is, minus 0.5625. Okay, so what does that actually mean? It means that your demand for barrels of oil went down by that much. So whatever this one oil broker is that's looking at the number of barrels that he sells in a day. On average, by raising his price from $40 to $41, he can figure on selling a little more than 1/2 a barrel less in the next day. Okay, we'd probably go ahead and round that up and say, you know, he's selling 1 less barrel. Yeah. Okay. All right, so then some of the problems that you're going to see some of on the assignment, I'm going to give you a function and ask you to figure out where it's increasing or decreasing, and then also to figure out where it's concave up and concave down. So let's take a look at doing this. We'd already seen the procedure for doing increasing and decreasing before, and so this is going to be a little bit of a refresher, and then I want you to see how it parallels what we do for concavity as well. So we have to figure out f prime of x, and this is a polynomial, so we just have to use the product rule. We just have to use the power rule. And we get 3x squared minus 50x plus 2. Okay. We said previously, increasing is where f prime is positive, decreasing is where it's negative. The only places it can change is where f prime is either undefined, polynomials are always defined, so we don't have that, or equal to 0. Fortunately, that's a quadratic, so we can go ahead and solve that. And being that I have worked this out 20 times already, I'm going to just go ahead and write down that that is 25 plus or minus the square root of 619 divided by 3. So you have 2 solutions for it. If you're wondering about estimates, the one where you subtract is about 0.04, and the one where you add is going to be about 17. Okay. So we will think about dividing up our number line at those points of the 25 minus the square root of 619 over 3, and the 25 plus the square root of 619 all over 3. And we needed to some test points. So a good test point to the left of that positive 0.04 is going to be 0. A good test point to choose in between would be where x is equal to 1. Why 0 and 1? Because they're nice numbers. And then over here, like 20, because, you know, they're nice to plug in. So when I get f prime of 0, I'm going to turn out to just get 2. And when I do f prime of 1, okay, that's going to be a little bit harder. I'm going to end up with 3 minus 50, so negative 47 plus 2, so negative 45. And then my f prime at 10, well, okay, that's kind of yucky. 300 minus 50, so 252. Okay, so positive, negative, and positive. So I'm going to report on increasing, and I'm going to report on decreasing. I think I'll write the decreasing down first because it's the easiest to write down. That's this here in the middle. Our test point was at 1, but we need to report the whole interval in between. It's not going to change sign anywhere except for those values. So from 25 minus the square root of 619 over 3 up to 25 plus the square root of 619 over 3. And again, the round parentheses to indicate that it's not including those. All right. So then for increasing, we're going to be choosing the stuff that's over here to the left and stuff that's over here to the right. So the way we express to the left of something is to go from minus infinity up to that number, 25 minus the square root 619 over 3. I probably should have chosen nicer numbers. Sorry. And then from 25 plus the square root of 619 over 3 up to plus infinity. And we put the u between them to mean we want everything that's in both of them. Okay, yay. Now for concave up, concave down. oh, damn it. In one of the earlier iterations of this video, I made a little animation. I'm sorry, I'm just not going to include it because that is extra work and I'm tired of doing it. I'm sorry. So when we talk about concave up and concave down, what we're going to be thinking about is where's the second derivative, positive or negative. Concave up is where the second derivative is positive. Think about a parabola. A parabola that opens upward has concave up. A parabola that opens down has concave down. So it's just which direction is it curving towards, okay? So for what we need, then we need to get f double prime of x. All that means is take f prime of x and take its derivative. So for us, that's 6x minus 25. Is that right? 6x minus 25. Ha ha. Y'all might spot that I copied my number wrong. That was supposed to be 50. So this would not be 6x minus 25, it would be 6x minus 50, okay? That can only change sign where it is undefined. Polynomials are always defined, or where it's 0. So we set it equal to 0, and we solve to get our x is equal to 25/3. So we think about our number line. We think about 25/3, which is somewhere around 8, okay? And we're going to need to sample something smaller and sample something larger. If there were more dividing places, we'd have to get things that are between. But we just needed to check something smaller and something larger. So smaller, x equals 0 is in there. Larger, x equals 10 is in there, okay? So f double prime of 0 is going to be equal to negative 50, which is negative, last time I checked. So f double prime of 10 is going to be equal to 60 minus 50, positive 10, and that's positive, okay? So this means that when we talk about concave up and concave down, that we can say that from minus infinity up to 25/3, okay? That 25/3, by the way, is referred to as a point of inflection. The place where the concavity changes is referred to as a point of inflection. And then concave down is going to happen from, wow, I'm sorry, folks. I just wrote that in totally the wrong place. Sorry. The concave down was where it was negative. So that should go over there. Yeah. And then concave up is going to go from 25/3 off to positive infinity. Okay. If you looked at the graph of the function, it would look kind of like that. And 25/3 would be right there in the middle where it changes, where it's curving. Okay. All right. So that's what we're looking at doing on those. And I want y'all to make sure that you spot that it's almost exactly the same thing as doing increasing and decreasing. It's just with the second derivative as opposed to the first derivative. So, all right, let's take a look at another one here. This one we're going to have to use the quotient rule for. All right. So the g prime of x that we're going to talk about here for our quotient rule, we'll say derivative of the top, that's e to the x, times the bottom, that's x, minus, now the top without a derivative, and then times the derivative of the bottom, so 1, divide that by the bottom squared. So that you can factor an e to the x out of and have x minus 1 and x squared, okay? Now, it can only change sign where either it's undefined
or where it's equal to 0. If you look at that denominator, it makes it undefined at x equals 0. If you set this equal to 0 and solve, only numerators can make things equal to 0, and e to the x can never be 0, so we get x equals 1. So I'm going to have my division points be at 0 and 1. Notice I put them in order. If I'd gotten -1 and 0, I'd put -1 to the left, right? -1 to the left, correct. And now for my sample, I need to check at maybe -1, maybe 1/2, and maybe 2. Now, if you chose different points, fine, choose whatever you want. Choose a million if you want to, but you have to carry through with the calculation. So just be aware of that. So g prime of -1, I'm just plugging back in there and I get e to the -1 times -2, and then divided by -1 squared is 1. So that's -2 over e, and that will be negative. Then if I do g prime of 1/2, what do I get there? E to the 1/2, and let's see, 1/2 minus 1 is -1/2, divided by 1/2 squared is 1/4. So I end up with a -2 e to the 1/2, and that's also negative, okay? And then g prime at 2, I'll have e to the 2, and 2 minus 1 is 1, divided by 2 squared is 4, so we end up with 1/4 e squared, and that's positive. So we'll have to line out increasing and decreasing. And you can see that the sample point that got us increasing was here at 2, which means all the stuff to the right of 1, we've got something that's increasing. So 1 to infinity. Insofar as decreasing, we've got 2 times that happened, and you have to keep in mind that you can't say it's increasing or decreasing at 0 or 1. At 1, it's making the change between increasing and decreasing. At 0, it's just undefined. So we will talk about going from, I need some ink there, dude. Minus infinity up to 0, but not including it. And then going from 0 to 1, okay? If you do a quick sketch of this, it looks somewhat like this. Okay, so that it is decreasing there, and then it's decreasing here. It's not decreasing while x is equal to 0, but you know, it is decreasing in those intervals in between. All right. So that gets us our intervals where something is increasing and decreasing. So now we're going to look at what to do for concave up, concave down. Now, this gets a little bit convoluted because of the fact that our numerator is not just a single term this time. So when we calculate our g double prime of x, we have to think about taking e to the x times x minus 1 and whatever its derivative is, and then multiplying by x squared, minus e to the x and x minus 1. Don't take the derivative, but take the derivative of the denominator. You get that 2x. And now our denominator, which was before x squared, has to be squared again, so it's x to the 4th. If you notice, you could factor an x out of the whole thing there and get a little bit of cancellation. So I'm going to try to do that as a quick step here, and that may cost me needing to write this stuff all over again, but so I'm going to put the x here and the x to the fourth, and then I'm going to do a cancellation, and this becomes 3 instead. All right, so then this upstairs there, this part, the e to the x times x minus 1, you have to take its derivative, and that requires the product rule. So take the derivative of e to the x, and you get e to the x, and you leave the x minus 1 alone, plus, now you leave the e to the x alone, take the derivative of x minus 1 and get 1, and all of that still gets multiplied by x afterward, and then minus. I'm going to go ahead and do the distribution in here on this part. So I'll have a 2 and an x and an e to the x, and then a minus a negative 2 e to the x. All this divided by our x cubed. Ugh. And now we're going to have to do our distribution here and have x squared e to the x minus minus x e to the x plus x e to the x minus 2x e to the x plus 2 e to the x. That looks like a terrible mess, but we have these two parts that will cancel out, and then we have this being equal to, I'll factor out an e to the x and have x squared minus 2x plus 2, and then on the bottom I'll have x cubed. Okay, so in order to have this change sign, one of the factors has to change sign, and so you can have that happen by any one of them being undefined or being equal to 0. So the e to the x is too nice. It's always positive, so we don't have to worry about it. This x cubed, though, at x equals 0, it's going to make the function undefined, and so we could be changing concavity there. This part, when you set it equal to 0, it gets a really nice solution of 1 plus or minus I. As you hopefully have noticed, we're not messing with imaginary numbers in this class, so I'm going to throw that out. So the only place we're going to change concavity at is x equals 0. And so we have to test some place where the x is negative and somewhere a place where the x is positive. So g double prime of -1 and g double prime of +1. Okay, just choose the easiest numbers you possibly can. And for -1, you'll get e to the -1, and then this -1 squared, and it will be 1, and then plus another 2, so you end up with a 5 there, and then divided by our -1 to the third power is -1. So this does end up being negative. And then when you plug in the +1, you end up with an e to the +1 and the 5 again, and a 1 down here, so this is positive. So we have to say where it is concave up and where it is concave down. And the concave up is going to be the place that the second derivative is positive. So the interval that included x equals +1, so to the right of x equals 0. And so concave up will be 0 to infinity. And then concave down will be -infinity up to 0. So did I try to draw a picture of this on the previous page? Yeah. So see how that picture is kind of curving down here, concave down, and up here, concave up? That's exactly what we've calculated and found out. So I think that is the last of my examples. It is. And so I'm going to stop sharing here. If I remember to, I will try to show you all that animation in class. I have it on a different computer than what I'm sitting at the moment. And I'm not going to record this a 5th time. So, all right, see you all in class. If I can figure out how to stop the recording. See you in class.